Section 21.4. In this section, we're going to learn how to calculate the electric potential for different cases. This is one of the most common cases. We have the two plates, the parallel plates, and capacitor is called, and one plate is negative, the other one is positive, and they both have the same amount of charge, positive and negative. And this sets up a uniform electric field between the two plates that we saw before. This field is given by the amount of charge on one of the plates divided by the area and divided by epsilon zero. Here the arrow and this unit vector are denoting the fact that the arrow denotes the fact that the field is a vector, and this is the direction of the vector. It's pointing in the x direction, in the negative x direction. Well, now imagine that you have a positive charge and you're pushing it towards this point at a distance x away. It begins at x equals 0 and then it goes all the way to x. Of course, we have to do work because positive charge would not want to get separated from the negative charges, and much less would want to get closer to the positive charges. So we have to do some work. We saw before that the electric potential, as well as the potential energy, depends on the position on x. We found that it was given by this. This is the electric potential, and is going to be given by the field times the distance, the displacement. And given that the field is given by this, then it's going to be that times x. On the other hand, the work done in pushing the charge from x equals 0 to x equals x is going to be given by the work equals the difference in electric potential energy, which is force times distance, and we go on, and we get to the same that we knew before, that is going to be the charge times the difference in electric potential. More on the same. The electric potential between the two plates is going to be given by this, where d is the distance between the two plates. The electric potential at any point in between is going to be given by this, where x is the position with respect to the negative plate. And the electric field we can obtain by inverting this. The electric field is going to be given by the difference in electric potential divided by the distance d here. And this is telling us that E, we used to measure the electric field in terms of newtons per coulomb, and now we can measure it also in terms of volts per meter. So if you do all the simplifications, you will find out that volts per meter equals newtons per coulomb. Well, looking at what we had before, turns out that the potential will depend on x being the distance from this plate that we're arbitrarily setting down to 0 volts. So as we move in x away from that plate, the electric potential is going to be increasing just like linearly with x, just like we have here. So all the points that are at the same x away from this plate are going to have the same electric potential. So like, for instance, we can draw this plane here that that has 0.5 volts. All of the points there are at the same potential, 0.5. And we can continue moving, and we're going to reach one plate at which all the points are at 1 volt, and then we can make it all the way to the positive plate, and that one is going to be 1.5 volt. Sideways it would look like this: the negative plate here, the positive plate there, and these equipotential planes are going to be in the middle. We can draw the voltage as a function of the distance away from the negative plate, and we can see that it's just a straight line, like dictated by this. So all the points at an equipotential surface have the same voltage. That's going to come handy later on. Let us look this video in which they measure the potential. Well, that tells you how the potential varies between two parallel plates. Let's look at this example. A parallel plate capacitor is constructed with two discs separated by 2 millimeters apart. So this distance is 2 millimeters. And it is charged to a potential difference of 500 volts. So if this is 0, then this is 500 volts. A proton is shot through an opening here with a given speed, 2 times 10 to the 5th meters per second. And what is the farther distance from the negative plate that the proton reaches? Well, we have to understand something here. This guy is being positive, doesn't want to move away from the negative charges, is being forced to move towards the positive charges because of the velocity that it has. But it will slow down until it reaches a stop. It is like throwing a rock into the air. It goes up, up, up until it stops and then comes back. Well, this proton is going to do exactly the same. And the question is, how far does it go? Well, we can solve the problem by using conservation of energy. In the beginning, it's going to have 0 potential and some kinetic energy because of the velocity. But in the end, it's going to have 0 kinetic because it's going to be at rest, and full potential energy. So from there we can calculate that, we can find the final X. So we say initial energy equals final energy. We know that in the end the velocity is going to be 0, so the kinetic energy in the end is going to be 0. So from here we can solve for the final potential energy, and we have we're missing the other half there. So from here we solve for the potential energy, which is charged and del V, and then x over d. This is the potential energy at a point x at this point. And from here we solve for x. So x is going to be given by 1/2 mv squared, the initial velocity, times the distance divided by the charge and the change in potential. So we calculate that, and it turns out to be 0.84 millimeters, much less than the 2 millimeters, less than half. So the drawing is not to scale, it should be around here, less than half. Synthesis. The plate capacitor, it has electric potential and an electric field. The electric potential of the points inside the capacitor will be given by this, where x is the distance to the negative plate, and the field in between is going to be given by the charge divided by the area divided by epsilon zero. So the voltage at any point x is going to be given by that. Or if we know the voltage between the two plates, the difference between the two plates, then we can just use that and multiply times x over d. Because if we set x equal to d here, that's going to give you the full difference in electric potential. So the electric field is given by this, or it can be obtained this way. Well, changing our system, moving away from the two parallel plates, let us now look at what happens if we have two charges, 2-point charges. And of course there's going to be potential energy between the two. There's going to be one will be creating an electric potential somewhere around it. And let us first answer this question. We have a fixed particle Q at this point, and we have a movable particle Q0 at point A. And the question is, will this particle move by itself from point A to point B? And the answer is yes, of course, because it doesn't want to be close to this other charge, and there's a repulsive force between the two, which is going to push it that way precisely, and it will at some point pass through B. So the answer yes, which means that the field, not us, is doing the work. And of course the potential energy decreases because it will do it by itself, so it is just decreasing the potential energy. What is the work done? Well, the work done is going to be force times distance. In the previous case, when we were dealing with a uniform field, we used this. Work equals force times distance. Except that the force was constant because the field was constant. But here, the field is not constant because the force is not constant. The force depends on r squared. In other words, the force that this particle feels at this point is going to be stronger than the force that it feels midway. It's going to be stronger than the force that it feels on point B. So we cannot use this one directly, but in order to use it, we have to split it into many small segments and add up all the different amounts of work done in moving through those segments. And that requires calculus. And what you end up with is something that looks like this. The work done in going from point A to point B is going to be given by KQQ, both charges, times all of this, with the negative sign just to denote who's doing the work. So it's 1 over the final radius minus 1 over the initial radius. Again, this work will correspond to a change in electric potential energy. So we have that, and the change in electric potential energy is going to be the final potential energy minus the initial potential energy. Equating these two, we can get an expression for U that will look like this. So U at a point, the potential energy, the electric potential energy, at a point R away from this charge is going to be given by this. Look at the similarity with Coulomb's law. Coulomb's law would have an R square right here instead of an R. And it would be a vector. In this case, it's just a number. It doesn't have any direction. Energy does not have directions. So this is the second method that you know on how to calculate potential energies. The first one was for parallel plates for a uniform field, and in this case is for point charges. Again, is the electric potential energy for 2 point charges. We can represent that graphically if we just plot it as a function of r. So it would be u, it would be, and r goes like this, 1 over r. And you can see that if r is extremely large, then you're going to be dividing this by something very large. Is going to give you something very small. So u tends to be 0 whenever the two charges are separated. Like when you have one charge here and another one charge far away. Now look at the fact that here we don't have absolute value bars. So we have to use the sign of the charges. And in this case, for instance, one is positive, the other one is negative. So the product here is going to be negative. That's why if this is 0, we are representing the curve as a negative curve. Again, u is not a vector, doesn't have a direction. The charges use their signs. So in other words, u can be negative. R is not r squared. Don't get confused with the power. U negative energy means a bound system. Quick check 21.6. We have these two charges, a positive charge and a negative charge. They are released from rest. And as they, of course, they're going to be attracted to each other. They're going to get closer. As they do, a positive potential energy becomes more positive. A positive energy becomes less positive. A negative potential energy, in other words, there is some potential energy, electric potential energy, and if it's positive, is it going to become more positive? If it's positive, it's going to become less positive. If it's negative, will become less negative or more negative, and so on. So I'll give you some time. Please pause, think, and answer. Well, we have in this case is a negative potential energy because it has one is a minus charge, the other one is a positive. So the sign is going to be negative, all of it. And as the distance gets smaller, we're dividing by something smaller, making this larger. So it's going to be negative, but it will be getting larger, which means that it becomes more negative. Finding the escape velocity. We have a negative charge and a positive charge, and they are supposed to be elementary particles. One is an electron, and the other one is a positron. A positron is a positive electron, same mass, same charge, but only positive. And to be shot out back to back with equal speeds. So this one is being shot this way, this one is being shot that way. Of course, if they are not shot fast enough, they will attract each other, and this one will move away and then stop and then come back and annihilate with the electron. By the way, it produces a flash of light that is used in PET, positron electron tomography. But the question is, what is the minimum speed that this one must have in order to escape and not bounce back? So what we have to do here is to calculate by means of conservation of energy and calculate the point at which the kinetic energy is 0. In other words, when the velocity is 0. Any speed larger than that one will give you will allow the particle to escape. In other words, if v is too small, this particle is going to move away and then come back. And if this is large, then this will be able to escape. So in the end, if they escape, in the end, they will have they will be far away, so the electric potential energy is going to be 0. So we have conservation of energy. The initial energy equals the final energy. So the initial energy is going to be 1/2 mv squared. But we have two particles, so we have to multiply times 2 for the total energy of the system. And the final potential energy is going to be 0. And the from here we can solve for the initial velocity needed in order to have this side equal to 0. So we have that the velocity is going to be given by the square root of I divided by m. Summarizing, we initially have two charges separated by 100 femtometers. A femtometer is 10 to the negative 15, and they have some velocity. And you want this velocity to be such that they will separate, and when they are far away, they don't come back. So you want the velocity far away to be 0, both of them, and of course the potential energy should be 0 when they are separated far away. So the final state is going to be kinetic energy plus potential energy equals 0. So you want this is your equation. The kinetic energy is going to be 1/2 mv squared times 2, because there are two of those, a positron and an electron. And this is going to be equal to minus the initial potential energy. So from here you solve for the velocity needed. And it turns out to be 5 times 10 to the 7 meters per second. Well, now that we have the potential energy between two point charges, we can go ahead and calculate the potential, not the potential energy, but the potential of a point charge. So we have is this divided by, remember what the potential is the energy per unit charge. And in this case, it's going to be the energy divided by one of the charges. So we get this. It is similar to what we had before. Again, we're using the sign here, and we don't have a square here. And this is a number, it's not a vector. If we plot it as a function of r, we see that it goes like 1/r. So it will decrease like that. And all the points that are the same distance from this charge will have the same value of v. So we can draw, if we have a point, we can draw, like for instance, if we have this charge, then all the points that are at this distance will have the same voltage. We can call that sphere an equipotential surface, or this one, or this one. We can put it as a map in 2 dimensions, and all these points are the same electric potential, and so on. Continuing with the potential of a single charge. What is the electric potential 1 centimeter away from this charge? Well, we know the constant, we know the charge is 1 nanocoulomb, and we know the distance is 1 centimeter. You will have to put it in meters, and then we can calculate it. And next question is, what is the potential difference between a point 1 centimeter away and a second point 3 centimeters away? Well, we have to calculate both V at 1 and V at 3, and then take the difference. So V at 1 is given by this, is again KQ divided by R, KQ divided by R, KQ divided by R gives you 100 volts. And for the other one, I didn't calculate it, but it's just doing it for 3 centimeters. Okay, quick check 21.11. We have a point A and a point B, and this one is in the presence of a charge, so it has a potential V sub A, and this one has a potential V sub B. What is the ratio of those two potentials? Well, pause, think, and answer. When I say pause, you might mean pause the video. Well, just a matter of calculating V sub A and V sub B, and we can see that it's gonna, when you take the ratio, the constant, the charge will disappear, and we end up having this divided by that gives you 1/3. This is another interesting case. If you have a charge, a sphere, and you charge the sphere, and the question is, what would be the potential at a distance r away? Well, it is not explained in the textbook because they skip talking about Gauss's law. But Gauss's law tells you that the potential produced by this uh, spherically symmetric object is going to be equal to the potential produced by a point charge. So it's kq divided by r. And all of this is valid for the outside because for the inside is a different situation. And the radius of this sphere is going to be capital R. So this is valid for little r larger than capital R. For r larger than capital R, this is how you calculate the electric potential of a uniformly charged sphere. And if you do it on the surface, you have to use capital R for this. Now, we learned before that the field inside of such an object, even if it's hollow or if it's a solid, being a conductor, we know that it's going to be zero. The field is going to be zero. So there will be no change in potential as we go from any point on the surface to the inside. Remember, V equals the field times the position. So in this case, the field is zero. It's a uniform field equal to zero. So because of that, all the points inside are going to be exactly the same voltage as the points on the surface. And so for inside is going to be the same as this. We can turn things around and ask what is the charge needed to have a given voltage. So from here we can solve for the charge, and it's going to be given by this. So the field, as I said, is equal to zero. So for inside in the spherical object, the inside will not change, the potential will not change, and we end up having the field inside. It will be given as, will be equal to the field on the surface. Summarizing, we have two different expressions for the potential produced by this charged sphere. One is going to be for the outside, this one here, and one is going to be for the inside. This is constant. This is varying with as a function of r. So if we plot v as a function of r, and this being the radius of the sphere, is going to be constant at some value, and then we'll start decreasing as 1 over r. We have, in this case, we have 1 centimeter diameter sphere that has been charged to 1000 volts. First question, what is the charge of the sphere? Well, we just saw how to calculate the charge, provided that we know the voltage. It's going to be kq divided by r, so the charge is going to be Vr divided by k, Vr divided by k, and it's going to be the radius, which is half of this, is going to be half a centimeter, put in meters, is all of that. And then the voltage is 1000 divided by the constant. So that requires this, to charge this sphere to this voltage of 1000 volts, requires 0.56 nanocoulombs. But then the real question is, we have a proton released from rest at the surface of this sphere, and of course, being positive and this being positive, this will move away. And the question is, what is the velocity, the speed that it has when it is 1 centimeter away from the sphere? So again, we have conservation of energy. Initial kinetic energy is going to be 0, and the initial potential is going to be 1000. Later on, it's going to have some potential, and out of that equation, some potential and some kinetic energy, and out of that equation we can solve for the speed. The initial kinetic, the initial potential is going to be equal to the final kinetic, the final potential. Initially it's at rest, so the initial kinetic is 0. Initially it's going to be this is going to be 1,000, and the voltage is going to be 1,000. So we multiply the voltage times the charge of the proton, and then it's going to be equal to the final kinetic 1/2 mv final square plus the potential at that point, which is going to be given by this, except the distance has changed now to r plus 1 centimeter. So we have to put it in meters, of course. So out of this equation, this equals this, we want to solve for the velocity here. So we do that here, and we get, now look at the fact that in this case we have a ratio of r divided by r plus 1. So the whatever units are here are going to be the same units here, so they will cancel. In other words, if we decide to use centimeters here, and we use centimeters here, it will give us the right answer. We don't have to use meters and meters, because in this case they would cancel, but it would work in any units. Part C, when the proton is 1 centimeter away, what is the kinetic energy in electron volts? Well, 1 centimeter away, we just calculated the velocity, so we can calculate the kinetic energy in joules, and from there we go and get it in electron volts. So we just calculate the velocity, we plug it in, we get the kinetic energy in joules. This is in joules, and then we divide by 1.6 times 10 to the negative 19 to get it in electron volts. Another problem, a proton is fired from far away towards the nucleus of an iron atom, which we can model as a sphere containing 26 protons. The diameter of the nucleus is this. What initial speed does the proton need to just reach the surface of the nucleus? Well, the problem is that we have a proton which is positive getting closer to a bunch of protons which are positive, so that it will be decreasing its speed, and if the initial speed is not large enough, it will get to a point and then come back. But what we want is for this to go exactly at the surface and have a zero velocity there, come back at that point. Well, we can set up the equations of conservation of energy, and we have the initial kinetic energy. Far away means that this is zero, the initial potential energy is zero, and the final kinetic energy is going to be zero, because it's going to be exactly touching when it turns around, and the final kinetic energy is going to be just the product of the potential times the charge. So from here we can solve for the velocity, the initial velocity that the proton must have. Plug in the numbers. This is the constant, this is the charge of the 26 protons, this is the charge of one proton, this is the mass of the proton, and r is the radius of the nucleus, which was given right here. I mean, this is the diameter, so we had to divide by 2 for 4.5. And this gives you the velocity needed, 1.171 times 10 to the 7th meters per second. Well, kind of summarizing here, we have a charged sphere, and it produces a potential outside, it produces a potential inside. The potential is given by this, and on the surface is given by this, and inside is also given by that. Checking these concepts. What is the electric potential energy at the surface of the sphere? Well, you're going to have to use your calculator for this one, but pause, think, and answer. Well, we can, we want the potential at 5, The potential at 5 is going to be given by this, but we do not know what is the charge. But we do know that 15 centimeters away, the potential is 30 volts. So from here, we obtain the charge as being given by this, which is 30 volts times the distance, and we use it here. And in doing that, we end up with 90 degrees. Now, it stands to reason that the electric potential will be decreasing as we move away from the sphere. So it will be increasing as we get closer and closer. So here is going to be 90 when this one is 30 at that point. Finding the potential of two charges. Well, finding the potential of two charges is basically the same as finding the potential of one plus adding the potential of the other one. So the potential that this produces at this point and the potential that this produces at this point is are going to be added. So we can factor out the K, simplify the calculation. It's going to be this charge divided by this distance and this other charge divided by that distance. Gives you 140 volts. Look at the fact that one is negative, so we have to use a minus sign there. In general, for many point charges, the potential produced by all those many charges should be just the addition of all the individual numbers. Well, another question. Rank in order from largest to smallest the potential difference V12, V13, V23. Well, the question is, what is the difference in electric potential between point 1 and point 2? What is the difference in electric potential between point 1 and point 3 and point 3 and point 2 and point 3 and so on? Well, we have three different answers. One that says that the difference between 1 and 2 is the same as the difference between 2 and 3 is the same as the difference between 1 and 3. The second answer says the difference between 1 and 2 is the same as the difference between 2 and 3, but is less than the difference between 1 and 3. And lastly, the difference between 1 and 2 is larger than the difference between 1 and 3. So pause, think, and answer. Well, just a matter of calculating. The difference between 1 and 2, given that these 2 points are at the same distance from the charge, the difference between those two is going to be 0. And the difference between 3, this is 2 and 1 have larger potentials than 3. So V3 minus V1 is negative, and V3 minus V2 is negative. And V13 equals V23, because they are the same distance from the charge. At which point or points is the electric potential 0? So we have different points, point A, point B, point C, point D. And we have the electric potential is being produced by this charge, which is twice as big as this one and positive, whereas this one is negative. So remember the potential is KQ divided by R, and we're adding for these two charges. So here you have to think whether, for instance, this point here, is it possible that I can have 0 electric potential here? Well, probably not, because it's too close to this one, it's too far to this one. They're going to give opposite contributions. This one is going to give a positive contribution to electric potential, whereas this one is going to give a negative contribution to electric potential. Except that this one being too far will not cancel the one from this one, and so on. So please look at the drawings, look at the dots, and pause, think, and answer. Well, it has to be, if anyone is going to have to be this one here. because it is closer to this one, that needs to be closer to the negative charge to compensate the fact that this is twice as large, but it's twice as far. So that gives you the exact cancellation that you need. Another question, we have these four charges here, and they are separated by, they are placed on the sides of on the corners of a square. What is the electric potential that they produce at the center of the square? Well, it is 0, and I don't have to explain much on this one because this point is going to be at the same distance than this one, than that one. So these two cancel each other, and those two will cancel each other. And this is it for section 21.4. This is not correct, it should be 4. And I'm assigning these conceptual questions as homework. This multiple choice, problem 2, and problem 16, 17, and 18.